Thanks for the invitation. This is a very exciting conference. Can you everybody hear me? Yeah. This is a very exciting conference because I don't know many people, and it's a bunch of very new stuff. And right, so I'm very happy to be here. I first heard about Victor Chapoy in 2004, when after I had written a paper with Graham Niblo to explain Sagiev's theorem that codimension 1 subgroups and cat-0 cube complexes were basically the same thing. And we wrote this paper to clear a misunderstanding with the French community who didn't realize that wall spaces and cat-0 cube complexes were the same. And after I'd written this paper, without mentioning Victor's work, which was actually prior to this paper, somebody told me that what he had proved was that median graphs were the same as cat-0 cube complexes, and in fact, codimension 1 subgroups and median graphs and wall spaces, you can kind of quickly see that it was the same. Back then, I was kind of disappointed. You prove a result, and then it's like climbing a mountain, and then you have the feeling that somebody comes from the back and tells you, hey, there was a bus up there, you sucker. But in fact, now I realize that it's really nice and it's really important to have several proofs, several viewpoints of different things. And of course, my only regret is that we didn't mention Victor's work in this paper. Right, so talking about different viewpoints on the same subject, that brings me to my topic today, which the title is Horospherical random graphs. So the paper I'm going to talk about just appeared on the archives. And it's a paper that's unlike whatever I've done before. And it's also a paper that doesn't really have a theorem. And I'm not really sure it's math. There's some math. So anyway, this is, and in fact, even though it's not written in the paper, it's a paper about COVID. Of course, nobody wants to hear about COVID, right? We're here to think about math. The last thing we want to think about is COVID. But as we all lived through it, so some years ago, there was this shutdown, and something completely new and unexpected happened, and we were all at home, and I'm sure that most of us were ranting on how the government is not doing what they're supposed to do, and how this should be done like this. Anyway, I'm opinionated. I have opinions, and in fact, you can read. I write opinion pieces every now and then. But anyway, I have opinions, and I kept loudly voicing my opinions at home to my husband, who couldn't take it anymore. So I decided to write the math that was behind my opinion, and it's not new math. So anyway, so that's all I'm going to say about COVID. I didn't mention COVID in my paper because then if you put it on the archives, you get flagged, and then some people might have opinions on what you write. But the paper I wrote, there's no opinion in it. It's just math. And so it's math that discusses random graphs. So our title is Horospherical random graphs. So in random graph, you have several well-known models. The first one is Erdos Rainey, and basically you take endpoints, and then you add vertices. You take endpoints, and then you add edges with certain probability. And uniformly, doesn't matter where your points are located in your interval. And Other famous model include Gilbert graphs with point connected. So you connect the point with probability Pn if the distance is less than or equal to some number. You stop connecting points far away. And Penrose studied a class that he called soft geometric random graphs, where you connect points with a connection function phi, which is a map that goes from R plus to the interval 0, 1. And so that gives you the probability of connection between 2 points given by phi of the distance between those 2 points. And so in this setting, Erdős-Rényi is just the case. So yeah, Erdős-Rényi is just the case where phi is a constant function. And then Gilbert is the case where phi is, you have 0, here you have 1, and your function does 1 for a while and then 0 after. And soft, it can be anything. It just has to be below 1 because it's a probability. And so our case is, we study particular case of soft random graphs where we pick a function. We're going to restrict to piecewise constant functions. And we are going to grow the graphs, meaning that we are going to first look at this first piece to get a first graph, and then look at the second piece to get a second graph. And so you get a sequence G, which is gamma I, where I, can be finite or infinite. And for this sequence, we're going, so in this sequence, we start with a set of points, and then it's at each level, it's the number of edges that are going to arise or with some probability, and the union of all gamma I is that soft geometric. So our graphs are soft geometric graphs. They're just we look at the stages at which we built. Right, so what do we do with those graphs? Well, the goal is to keep track of the first eigenvalue of the Laplacian as those graphs grow. So lambda 1 is so as many of you might know, I'm a geometric group theorist. So for me, even if I don't say so, in my head, a graph is really the Cayley graph of a group. And so it's going to have constant valency, K. But this is not the case. But anyway, even if I just know that in my head, all my graphs are K-regular. So here I'm going to have the graphs are simplicial. And in my head, they're K-regular, even though in the simulation, they won't be K-regular. But Right, so what's the Laplacian? When you have a graph, you get an adjacency matrix, which I will denote A is Aij. And since I decided that my graphs were simplicial, undirected, and it means that this matrix has zeros in the diagonal and has, on each line, it has one, and only zeros. And it's symmetric, so it's diagonalizable. And so so lambda 1 is going to be the first eigenvalue of ki minus a. So that's something that a computer knows how to do. I mean, theoretically, I would know too. But so why do we care about this first lambda 1? It's because of lambda 1 is related to Cheeger constant, which is also called conductance. So what is this Cheeger constant or conductance? I denoted by phi gamma, which is the inf of the boundary of an element divided by the cardinality of S, or V minus S. My graphs are finite. So basically, this constant is going to tell you if you have your graph, this is my graph, and I take an S, and I'm going to try to cut it out. And I'm going to, so this conductance will tell you how expensive it is to to cut your graph in two pieces, to disconnect your graph. And, right. And you say that the graph, gamma G. So yeah, my graphs are gammas and Gs. Anyway, I only have graphs. I might not even have groups in this talk, even though you know that they're in my head. Right. Right. And you say that gamma is a C expander if this constant is greater than C. And so can I use this one for real? The camera is going to follow me? Yes. Okay. So let camera follow me. You're not sure? Okay, so I still have some room here. I'm gonna do the room. So how does it? So what does it have to do with the first eigenvalue? There is this theorem. I think it's due to a bunch of people. They're all tenured, so it doesn't matter if I forget their name, I guess. Lambda 1 divided by 2, it just says that 2 lambda 1. Basically, this theorem tells you that lambda 1 is a good estimate for the conductance. The conductance is something that would scare off people trying to compute stuff because you have to find a min, an inf, and whatnot. So it's scary. So computers don't do that well. But what it says that the lambda 1 is a good estimate. And right. And so why do we care? Because of random walk. So what is a random walk? So a random walk is a sequence. You can? You think so? Okay, then I'm going to use this board. So random walk on X, so is a sequence xn of random variables, such that, but anyway, such that the probability to be at some point xn is equal to y, knowing that x0 to xn is some other sequence x0 to xn, is the same as the probability of xn being at y. It just depends on what happens at the step before. And it has to be 0 or 1 over k if d of x and y is different than 1. And so 1 over k, k is the valency of the graph. Again, I'm assuming that it's constant, but in fact, in the simulation, it won't be constant. But it doesn't matter. So, for those who know, it's a random, it's a Markov chain with some transition given by the graph. Sorry? Did you put 1 over degree of xn? Yeah, it's 1 of the degree of xn, exactly. And so how is it related with everything? Well, it tells you, the first eigenvalue, or the conductance, tells you how fast your random walk will converge to the uniform distribution, and this means how fast your random walk will have gone everywhere in your graph. So, of course, if you think that your random walk is a virus with some, say a theoretical virus that's immortal or has reproduction number 1, it's going to tell you how fast it's gone everywhere. The probability of xn is equal to x minus k over capital N. So this is the uniform distribution, is going to be less than or equal to lambda 1 minus 1 to the power n. This is the number of steps. So if you have a random walk on a graph, if you want to be sure that it doesn't go everywhere, what you have to do is try to have the first eigenvalue really low. This is called a spectral gap. You want to have spectral gap as small as possible. And so you can already say from here from the geometry that if you're in R2, if you're in a graph that vaguely looks like R2 and you cut out a piece of it, then you're going to have, if this is flat, well, the boundary of your ball, that's going to be like the square root of the volume of your ball if you're in R2. But if you're hyperbolic, the same set is now really difficult to carve out because you start looking like an exponential. Right. So recall. I think we've seen that hyperbolicity is for metric space is when triangles are uniformly thin. And in fact, any metric space can be embedded, not isometrically, in a hyperbolic space. This is a construction that you have in Gromov's book already, and you embed it as a horocycle, as a horosphere. So basically, you have your metric space here, which could be flat, and you can cross it with R. And on R, you put a metric that shrinks your metric space exponentially as you go up. So it means that you're going to land into a hyperbolic space where your metric space is now all curled up, like a horosphere. And the horospheres are given as level functions or of Boozman function. And anyway, you put and when you do that, what's happening, in fact, is that you take your graph and you take your metric space and you actually add shortcuts. Because here you go like this, but in fact, there is a shortcut. It doesn't look like a shortcut, but you know. And in fact, when you embed your metric space in a hyperbolic graph, you get a bunch of shortcuts. And while you do that, some sets that were previously had kind of low isoperimetric function suddenly get really high isoperimetric function. And so that's the idea. That's the idea that we discussed in this paper, saying that, well, when you have your sequence of horocyclic graph, you start with a graph on an underlying metric space that you build however you want, and then you keep adding shortcuts, kind of randomly, long shortcuts. You know, think of opening air travel and the shortcut that it brings. And right. And so we did a few simulations on how this changes the first eigenvalue. So I'm going to switch to the slides now. Right. Yes. So that's a good moment to mention that it's a joint work with my collaborator Austin Lawson, who's at Greensboro. Who really has I think he has a background in coarse geometry and data analysis. And right, so can I? Right. Right. So this is my first picture. Is one of my favorite group. It's a Z free product with Z2, and it's also a nice cat-zero cube complex. It's the universe. So the cat-zero. So the group is the fundamental cover of a torus where you add S1. And when and so you can see a copy of Z2. So that's definitely not a hyperbolic group. And this is a universal cover, part of it. So it's a tree of lines and planes. And if you think in terms of a Cayley graph or the one skeleton of the cat-zero cube complex, you will have big Z2 grids, and on each point of the Z2 grid, you have a Z line, and on each integer point of the Z line, you have a Z2 grid, and right. But it's definitely not hyperbolic. So, for instance, in this flat, you have pieces that you can easily carve out with not a lot of. It's not very expensive to remove those big pieces in those planes. And but I'm going to show you this embedding in a hyperbolic space. The embedding I told you about, Gromov discusses in his famous paper. So basically, I take my tree of line and space. I hold a plane and I shake it a little bit so like I dangle the whole space underneath so that I can see my plane. And then I'm going to build some kind of cusp. So basically Z2, and I take layers of Z2 and I build up the layers. And at each layer, I shrink the metric so that the distances become really short. And when you do that, and you look at the metric space you get, geodesics starts, they don't no longer travel in your base flat, they start going up the cusp. Triangles are thin. So here you can see the geodesics going up the cusp and kind of the thinness of triangles. And it kind of resembles, the geometry vaguely resembles this type of geometry. Even though that's really just an indication, it's not mathematical. And then you're going to take your cusp and you're going to glue it on your flat. And you're going to do that on every flat. And remember, there was a group action. So what happens on downstairs, if you take the quotient of this thing with all those cusps, you get this type of object, which is no longer compact, but has the advantage that the universal cover is going to be hyperbolic. And so here is some simulation where we started with horospherical graphs on a uniform distribution. So basically, you have you take a uniform distribution and of points, and then when you just have a small connection function, when you connect only points that are nearby. So people in random graph, something that they study is connectivity of the random graph. I didn't want to bother with connectivity of the random graph because it messes up the first eigenvalue kind of uselessly. So I just put high probability of close points being related, so I get some connected graph. And here we kind of looked. I don't think that this thing really tells you much. It's not, well, this thing doesn't, it's not the most, but anyway, it's just to see that we tried several connection functions, and we looked at how the first eigenvalue moves, and we also, some of them are kind of sparse in the sense that the percentage of edges is not very high, and you can also compute average clustering coefficients, and right, so this is not particularly illuminating, but we did another experiment. This is me at home being all annoyed at whatever new announcement the government makes. And so we tried horospherical graphs based in France. So what did we do? We downloaded this map from Wikipedia, and then I drew over it, and sampled points according to this.
What was the map? Population?
Yeah, this is density of population map from Wikipedia. So I have to tell you that my computing, my coding and computing and data savviness are very limited. Actually, they're very limited. Austin Lawson can do much more, but then it's always on one small computer, so. Right, so, yes, so we drew the most dense area and then sampled points according to uniform to normal distribution over the densely populated area that we roughly try to match the population, the actual population of the cities. And then we overlaid also a standard grid all over because of connectivity problems. We didn't want holes. And we tried two graphs. First, the first one is where any form of long distance travel is closed, but local. Everything is open locally. You can go locally. You can go wherever you want. And the second one is, so it's open locally, but on a smaller scale. And then it's kind of restricted after. And well, you can see that there is a huge difference in the first eigenvalue. There's not much difference in sparsity in the way we sample that's because of the way we sample the edges, and the max valency locally is for the graph where locally you can go everywhere is much higher. So, in terms of what you heard on the news about COVID transmissions, like don't see many people, this graph kind of tells you that you can see a lot of people locally and still have a very low lambda 1. But this is something we already know. Like, if the geometry is R2, your random walk is going to be slow. If the geometry is more hyperbolic, your random walk is going to be much faster. And right, so and so then we simulated a 100-step random walk on gamma. And you can see that on the first graph, where everything is open locally, your random walk, which here started in Lille, seems to stay in Lille. And the other one goes everywhere, really fast. 100th step has gone everywhere. And this is a, right, this is a, you know, so we, yeah, then I have some more simulation. But it was, you know, since we try to estimate stuff from data from you know, statistics of people flying and stuff like that, but we didn't have any good scientific way of doing our estimates. Really, this is really more heuristic.
Sarah,
Yes?
can you repeat what's the difference between gamma? What was the parameters that were?
So gamma is the one that has connection phi of r, and G has a connection P of r. See? I have a graph called gamma and a graph called G. I'm Swiss, you know, I'm neutral, so I'm trying to have everybody agree here. So, as long as there are graphs, yeah. Yeah, right. No, in my head, they're groups. Okay. But of course, you know, we heard a lot of about reproduction number, and as soon as you add some reproduction, here we had a walk. We couldn't put the walk anymore because then you have just a black square in your simulation. But so we put orange dots for the places that that the walk visits. Let's not call it virus. Let's call it walk. So this is when the walk replicates after, I think, 10 steps visiting a node not replicated before. Then we get, with entrance point somewhere in Lille, this thing doesn't go really far, whereas the same entrance, it just goes everywhere. And if we reduce more the long distance travel, which is, I try to get some sense on how the long distance travel was reduced during COVID. It was, yeah, I couldn't really have a, you know, a good, I couldn't have a really, you know, something that matches the actual data. But here's what we do is, first we reduce the long distance travel, but here by a factor 5, and we see how the lambda 1 diminishes. And here we reduced even more to start looking like confinement measures, like the first confinement measure. The confinement, we were trying to go back and see if there's any logic in the confinement measure that we had. And I couldn't find any logic or any, anything that will tell me this is how you should run the simulation. But anyway, we played a little bit with those numbers to see how you reduced your first eigenvalue when you reduce long travel.
What is the scale here? 10 in 100?
Yes, 10 is more. One is 100 kilometers.
1 is 100.
Yes. So 10 is roughly yes. 10 is roughly the size of France. Yeah. And so we run more simulation with those two eigenvalues. So you can see that when you really restrict, somehow Nice looks spared. Except that it's probably not the reality because the first place people go is Nice, right? And in fact, I could see that air traffic was reduced, but it was still there. We can see the plane going. And but if you look at the sites visited with a walk replicated every 10 steps, there's no difference. There's basically no difference. And right, so and that was basically my original rant, because we were confined, and I would go out within the allotted kilometer, and I could tell that the people from the yachts were here. I could tell that the airplanes were flying. I mean, some airplanes. You could see them. And you could see that, and you could still see tourists. We had tourists in Nice. While I was allowed this 1 kilometer, I could hear people speaking another language that was not, well, a tourist language, let's say. Right, and right. So the last simulation is this one. Again, it's not. It doesn't. It would be nice to be able to run those type of models on actual data. To see, eventually make predictions and try to have a better. Well, yeah, I don't know. I would be interested to see to understand how they took their decision to close, restaurants, or to close schools, or to close that type of travel, and to allow, who is really essential. Like, we were deemed unessential, even though we're probably the ones that needed to compute things, right? Anyway, so what's the simulation here? So the blue line, so gamma R is the graph that it's not in a random graph, it's a deterministic graph where everybody meets everybody within a distance R. So it's way more than reality. And the blue line explains how the first eigenvalue increases as your graph starts to be more and more starts to have more and more connected. And lambda 1 is the first graph, which maybe maybe it's unconfined. And lambda 1 prime is this kind of confinement that we had, where long distance travel is heavily restricted and partially shut. And then you can see where those intersect. Here is around 200 kilometers. The other one is 3.2. So this is what, and this was basically my rant, is that the confinements started closing stuff locally, trying to. We had such a big focus on super spreaders and having low valency. But if you do geometric group theory, you know that your expanders, you have very good expanders with SL3Z that's generated with 3 elements or 4 elements, whatever. Very, very low valency at each vertex, but still very good expansion properties. And those are the ones that are going to tell you how fast your random walk is going to go everywhere. As I said, it's a paper that doesn't really have a theorem, but it's my way of channeling my obsession with the news. So before I stop, I can maybe say a word for people who are roughly my age and that may remember another pandemic from their youth, from the teenage years, a pandemic that killed people, and that was largely attributed to behavior of prostitutes and homosexuals, two classes of people who had economical status below the rest of the population, so who could not have been responsible for the long-distance travel of the virus. And right, I'm going to stop here. Thank you very much for your attention.
Okay, so we have time for some questions or opinions. Yeah, please.
Yeah, did you try a model like the Kleinberg grid, where the probability to have a link between x and y would be 1 over distance of x, y?
No, we didn't do the 1 over distance.
I would guess that it would spread a lot.
Yeah, 1 over distance. Yeah, right. Because we tried the exponential one didn't. Yeah, so we tried a few functions here, but that's on the uniform distribution, and somehow I really wanted to do it on France so that it'll start to look personal, right? I wanted it to be personal somehow in the simulation. And it seems to me that the exponential one really stays with a low, but it decreases really fast. And I would think that 1 over distance will still spread.
According to Kleinberg lower bounds, just setting 1 over distance to some greater exponent would be sufficient to kill the thing.
I see.
And I mean, and even higher or lower could be hard for propagation.
Yeah.
At least for short paths.
Okay.
That's what he analyzed.
Yeah, so that's and I would definitely welcome any comments or explanation on previous related work, because it's totally not my area. I did my best to kind of read the existing literature, but I really suck at that. So if somebody can point out and explain existing stuff, I'd be very happy to.
2000, some small dwarf phenomenon.
Right. Yeah. So we looked a little bit about on the clustering coefficients of the graph we obtained, and so the clustering coefficient is actually the proportion of 3 cycles among all the neighbors, and it seems to me that you can change the clustering coefficient without affecting the lambda 1. It's in terms of, if you think in terms of a group, having a high clustering coefficient amounts to adding a bunch of short generators. It's not going to do much for you. Yeah.
What is this clustering coefficient again?
Clustering coefficient is, you're going to look, so you have a point, and you look in the link, and you count how many triangles you see among all the. So here, that's something you do. That's like a triangle missing, and wait. It's a measure on how complete the graphs are locally.
Thank you very much for your talk. Do you plan to continue work in this direction and maybe fuse this work with the epidemic modeling, with the existing models like SIRS and so on?
I don't know. Yeah, I have no idea. Yeah, I would love to. Yeah, yeah, I would love to.
Okay, thank you.
I would definitely love to have a little more computing power and data analysis power.
Okay, let's thank Indira again.